Perfect. Thank you again for me here. So in previous talks, we have kind of sketched an idea of how this analytic prismatization is going to be constructed, both from some desirable, let's say, at least abstract situation, from some first nice category of stacks, second some category of analog to delta rings, and a couple of functors that kind of factors through something in between. The last talk, in particular, we discussed maybe how the prismatization look like what were the kind of different locus you have, the underlying topological space, the prismatization of, say, a Riemann space, and so on. So in today's talk, the goal is to actually define this gadget. Definition. And to explain some first properties of this. So in order to give the definition of the analytic prismatization, we first have to introduce a little bit of language that say going to be necessary because of the world we are defining these objects in, like the world by these stacks. So let me start by introducing a very important object. This object that is going to be this notion of physically bounded ring. So recall that from the motivation of the Hodge space stack. So sorry, the Raman stack. We wanted this quotient GA over GA dagger, or this GA dagger with this intersection of negative 0, make it a fine line, to be a ring stack. We can actually know this with some structure of ring stack, and we can do some maybe fancy version of this transmutation and just construct the Raman stack from at least any reach. So this requires this guy to be GA ideal. Maybe let me give an example of why this is not true for any algebra. So we are working, although we work over algebras, solid algebras over Q. Then first examples of these things was this ring itself. So we call that this GA dagger was just a spectrum that, again, formally is just denoted this way. Of an algebra that maybe I'm going to keep denoting this way. That is, again, just a whole limit of Banach algebras. This. So what are the functions in here? Just share some functions at 0 of the analytic affine line. In particular, basically, you have this variable t, but you also have the constant guys. And well, this guy is ought to give you the elements of norm 0 in some sense over this way. So something to compute is that the functions of this G dagger of this algebra is actually just the ideal defined by this guy, which, well, in particular tells you that it's actually an ideal of this guy. So, okay, we want this ring, for example, to be part of the theory. We are going to consider, because well, it's also going to be the ring that represents this object. Now, just look at something like A to be this algebra, but where we have added another polynomial algebra. So now this algebra can specialize in any number in QP. Doesn't need to be a number. And what is worse is that this variable t cannot be bounded by any means, because being bounded should mean that basically you can extend the function to this variable to some kind of data algebra, to some kind of Banach. But this variable t is the algebra generated by this, far from being a Banach algebra, not even inside a Banach algebra. So actually, if you compute what this radical is for this guy, this exercise, it turns out to be the same as this one given diagram, which in particular is not ideal. So we need a kind of a systematic procedure to just get rid of these kind of samples and just consider things that maybe look like that, maybe look like data algebras, maybe look like explanation.
So when the root square brackets, that doesn't just use polynomials.
Yes, just mean polynomials in
Just polynomials.
Just
Not polynomials.
yes. That's exactly, you don't get anything. So a way to solve this is precisely with this definition of bounded range. So let me give a light definition of that. Again, is not too far from being the general definition, but well, technicalities are hidden in the actual definition, but actually just gives you the correct idea of what this value is. So maybe it's a definition. Let me maybe first just introduce some plate algebras. So for some positive real number bigger than 0. So let this QP P to the R dagger be the algebra of functions of a closed overconvergent disk of radius no P to the R. This one, again, is going to be this intersection of all the maybe affine disks of radius the epsilon. Or epsilon, I think it's more than. Yeah, so basically, I just taking instead of taking an affinoid data algebra or Banach algebra of radius 1, I just take the intersection of things that overconverge. I just take this over.
Sorry, Juan.
Yes.
Why is not an argument? For me, something very.
Multiplicative.
You cannot multiply by T2.
TI here.
T1.
T1 times.
Oh,
Fine.
sorry.
So you're taking now this kind of overconvergent algebra, so maybe instead of working with that spaces, you may work with the point symmetry. And this for things important the difference between the two. And second, so we say, so let A be a the algebra. And A an element in A. So this datum is equivalent to give a map from a polynomial algebra to A. So we say that the norm of A, maybe the p-adic norm, is greater than or equal to P to the R if this map F leaves, which is going to do what you need to do. To one of these algebras. here.
Just you say that the QP algebra.
Yes, always a solid QP algebra. Always.
Ah,
Always going to work in the category of solid. And well, we say that A is bounded. If all for all A and I, this norm P is smaller than the quantifiers. So, very complicated way to say that basically, well, an element is going to be bounded by this power of P. If and only if you have this extension to this algebra. And a bounded algebra is just an algebra where all the elements are bounded. So essentially, what is the idea behind it? We are taking all the algebras such that the map from the spectrum of A into the algebraic affine line, QP, which is just the spectrum of this polynomial algebra, is going to factor through the analytic affine line. It's just the union of maybe of this overconverging disk, or maybe just because produce.
can you look at the definition?
Yes.
Um,
Yes. So basically, well, A is bounded if any element is bounded. Just write in different weird way here. And an element is bounded if it satisfies this property for some real number.
Can I ask a couple of questions? So one is that these algebras of power series that overconverge.
Yes.
These are idempotent algebras over sort of
Yes.
polynomial thing, and that's the necessarily uniquely
Yes.
in so they have property.
Yes. So. But exist such a leaf that is unique follows since this map from polynomial algebra to this overconverging algebras is idempotent. Meaning that the tensor of this one itself is just itself. So this implies that you can lift it, there is only a unique way to lift this. So this makes it not that the will behave, but just actually a condition, a function, and an additional structure you can do that. So maybe again some different way to give an idea of what this objects look like. So do this.
Sorry, can I ask one more question?
Yeah.
So so you put the condition on each element of A, like each element underlying.
Yes.
So is it so is it not necessary to, or does it apply like some sort of analogous statement on all the like S points?
So yeah, so the actual definition, so this is what I say, this is just a light approach to this, but just at the level of elements, basically the basic idea of this definition. Maybe, okay, the subtleties on this is that this is basically just describing the point properties of your bounded rings. Because you're working in this condensed world, you need to specify points for each programmed set. So you need to make analogs of these definitions for all profile sets. Yeah.
To light condensed
Uh,
mathematics or to light in the human
In the
sense.
human sense.
Ah.
Yes.
So even in the case of light condensed
Yes.
mathematics, it's not in, so
Yes.
that's problem. So was it a definition or a pre-definition?
This was a pre-definition. We have written pre-definition. So this is a definition, but this one, maybe this one is a pre. Well, this is okay, but this is a pre-definition.
And the typical non-decounted just the such.
Yeah, this is basically going to be the typical multiple example.
There was before the word idea, there was we say it's about
Yes, so let me.
definition or
So all what is before is a definition, and this two points are going to be a pre-definition.
so. Tell us in if something is a
Pre-definition or not.
just tell us in
Okay.
So basically you want to replace the additive rule by the union rule. Which is something like this.
Yes, which is just the usual analytic finding. This is kind of the idea. We want to replace this one in the category of objects we are going to test. Just to, this one to be represented on the left. Right. So again, some idea which is maybe to keep in mind.
But we haven't yet, so a cube probably explains the idea correctly. But you didn't give it.
I didn't give it. No. I don't want to give it because it's going to introduce a documentation that we're not going to use.
Just one. So the predefinition has to be modified, but you are not going to explain it.
In the talk, no.
Not at the top, but maybe in
When the name else is written, yes.
it's already.
Yes. I mean, this is basically just making this idea formal, which is maybe not too important to actually get the idea of the construction that follows. So they keep in mind for a bounded algebra. It's not too far. In putting it. Banach algebras. This means that any colimit of Banach algebras, in any sense, is going to give you a bounded algebra, because well, to test an element or if a profile set is bounded or not, you can always just lift it to one of these colimit there. And if you kind of extend a little bit the notion of what a Banach algebra is, allowing this kind of profile sets floating around, this actually becomes true. This category is going to have some generators, which are essentially IP completions of pre-algebras of profile sets, for example, just take algebras. And you just take colimits of all sets. So again, just take this maybe as a slogan and think of your bounded rings as basically just colimit of Banach algebras. It's not too far from being the actual thing.
Sorry, can I ask, so if you have is it correct that if you have a P-complete solid ZP algebra and you invert P, will that would be bounded?
Exactly. So they don't make this precise, but they, as I can say, the P-complete set P solid algebra, then it's generic fiber. Oh. Basically, because any map to the point to this guy can actually be extended to the Tate algebra. So it's going to factor through an analytical function. When you divide by P, you just are changing the radius of the elements there. And it is true that these guys are just colimits of algebras of this form. This is actually all bounded algebra is just colimit of generic fibers of P-complete solid algebra. Okay, so we wanted to get maybe let bring B or bounded the category of bounded algebras. And something that we wanted to make concrete in this world was again the fact that this guy should be an ideal. So let me make that definition. So let A be a bounded algebra. So then, well, first you can define the elements of non-legal equal to 1. This is basically just again, maybe this should be a pre-definition because I'm just going to define the level of points of these things, not compromised sets. States on all the elements in A such that the norm of A is smaller than 1. Basically, all the elements such that I can extend the map from the polynomial algebra to this overconvergent this over this one. Second, we want to define this new radical. Again, this is a pre-definition because it just giving to you the number of points.
Sorry, by the problem with the spin-off, right?
Sorry?
Like this norm.
Yes, the norm respect to P with this one. And these are just the elements of A that have norm 0. But how you can write that? Well, we can write that as the elements of A that have norm smaller than equals to P to the R, or R. And an equivalent way to write down is basically just the limit of this right, basically just like anybody but the elements of the maybe
Take some connected.
yeah.
But because the limit itself, if you do derive limits, I think like the limit might itself not be.
Yeah, it could be the case that you need not connect. That depends if this guy is going to be complete or not. Or maybe you go to its rejection with the complete. So theorem. Also, you heard that actually this guy, the guy is more or less equal to 1, is a solid ring. Meaning that, as you would expect, you can like the sum of two elements of non equal to 1 is has not less than equal to 1, and of course it's table on multiplication. But even more, not just as a ring, as an underlying set, but you can actually promote it to a ring which is complete and solid. So this actually has a lot of hidden non-trivial step. Well, of course, these guys are solid. This is the kind of thing you will expect from working in geometry. You fix some values, the elements of some fixed norm. You can just add and multiply values of 1, and maybe you can just multiply by elements of 1 and keep the same norm. So it's not crazy. But what is more important is that if you take actually go to norm equal to 0, then this thing, idea of taking. Maybe this means that actually this guy is a push object of this one, right? And there is a stable on the multiplication of elements. So maybe from an heuristic point of view, it's not surprising because here you're taking elements of norm equal to 0, and here you're taking elements basically a finite norm, because you choose the ring to be bounded. If you multiply something of norm zeros with something of finite norm, or you get something which is. So now having this theorem, we can finally make sense of this GA modulo GA dagger as a ring star. So
Now, so here you assume A is a solid algebra already.
yes,
So the first part follows from that topology.
no, it's even not tautological just for that. You still need to produce a like proving that something is solid follows from some kind of completeness condition, or maybe follows because you can write this guy as a co-limit of solid guys.
Yeah.
So you still need to be able to produce this guy as a co-limit of solid modules. So it's not completely trivial.
So it's something like you have some little sequence and you know that it's summable in the A itself, and the question is why it's summable in the A
for example.
with.
So then I'm proving that this is just a ring. That's underlying ring is not hard to this and again it's hard. What is difficult is to promote this to actually complete like solid objects in the objects in the category we're working with.
And when you are saying it is complete object, you really mean like thing on the page? Or
No.
one page?
I need a solid.
Just to verify, A is A less or equal to 1 and doing 1 over. That.
First? Yeah, for the whole.
Yeah.
Yeah.
Okay.
Very well.
Yes.
So with this thing, we can make some definitions. First, or maybe later, a bounded algebra. Then the first thing that we can define is the reduction of this guy. So we basically construct something that looks like a nil radical. You can just kill the nil radical and get the reduced version of a ring in this setup. Like a reduction. A is double reduce if A is equal to its double reduction. So the natural map is an example. Let me state this as well, because it's actually also non-trivial to work these things. We're going to write right now. So let A be an element of A, and A bar its image in the reduction. Then for this guy, is going to be smaller than some real number R, if and only if it is in the quotient.
Maps, joint, yes, objects, serial maps.
Yes. So basically, if you have this element of the image here, any other like representative differs by something that has non-zero. So every possible way to do this with a certain norm, it's going to be the same as having it here. In particular, this radical, the reduction, 0. So actually, this is an idempotent construction. Maybe some remark. If A to the n is equal to 0, then it has norm equal to 0. Because well, this norm is multiplicative. Means that the usual nil radical during A actually is contained this radical. So this one is an enlargement of this radical. And this follows, or maybe it's also can be understood from the fact that this overconvergent neighborhood of zero is slightly bigger than the formal completion of zero, as this as analytic. So these are different ways to think about zero, and this one is larger than this one. But as we saw some examples before, these ones could have elements which are not important in the usual sense, just elements of norm zero.
So can I just have the question of the properties of the norm, this intrinsically defined norm? Did you say that it's so like the norm of A to the n is the norm of A to the n?
Yes. Sorry. So something that I should have said that is that this norm is going to be in multiplicative. Okay. I mean, like, yes. So at least norm of this is going to be just this, in the sense that something is smaller than something if and only if the other one is smaller. Okay, so
So you just mentioned, but what are examples are you looking at this?
this one,
Right.
when they are different, so let me give some examples. So maybe the first is let A be unusual state algebra. So basically just a quotient of QPT1 to the n. Then, well, turns out that if we look what happens with this nil radical, hey, this is just the usual nil radical. Maybe some other sample. If A is a algebra. Means that this thing is theoretically complete. Bounded. Then the nil radical A is actually equal to 0. Arrow again. Nil radical. Basically, just the intersection of 1 over the n multiplied by this guy as well, which is the same as the intersection. 1 over p to the n of that. Doesn't matter which version you take, when you work over convergently, these two are going to compare. And these elements are basically just all the elements that can be infinitely divisible by p in the form. So this is going to imply the first one here because we know that reduced state algebras are uniform.
Is that p to the n times?
Yeah, it's p to the n times. It's p to the n, 1 over p to the n times is just this bigger notation of a naught, basically.
Otherwise, that would not p to the n.
Because you're right. And an example where the nil radical is non-zero, well, you need to actually go outside the world of usual analytic rigid geometry. And again, let us take this example. Then the nil radical. This guy is basically generated. All the functions that come from 0 is basically particular, this guy has not nilpotent elements. I mean, still, does not these elements of norm equal to 0.
To clarify, if you have a Banach algebra and if you have an element of spectral norm 0,
Yes,
then that will be
an object in this nilpotent.
Okay.
Yes, yes.
and that doesn't have to be norm.
For the case of Banach algebras, it doesn't have to be nilpotent. Yes, in general, for data algebras, it does. For things that we'll go into later, it doesn't need to be nilpotent. Okay. Okay. So
So for doing the usual Banach algebra,
spectral norm equal to 0.
yes. Algebra of the mean.
Yes.
So you don't.
We don't do not related stuff, at least. I don't think we do. So maybe, well, I'm just going to use this time to again give maybe the formal definition of this RAM stack. So let me just take it's the Ricci space. Then X the RAM is a functor from this category of bounded rings. Going to land two sets. So we are going just to kill everything. Cannot. That maps a ring A to X evaluated in the reduction of X value. So similarly for the algebraic one, we just kill all these the potency things of the diagonal by just evaluating X in the reduction of rings. Here, the RAM stack is defined a similar way. So instead of looking at the algebraic radical, we look at the analytic radical. That would be a better analytic radical. Some final properties that I want to mention because we used programs.
And is this the final definition?
This is the final definition.
Without assuming X.
No, in any. Here I just take Ricci space to not introduce more notation, but this is for any analytics over Q. In particular, non-smooth Ricci spaces.
Always set.
It's always going to take values in set because you're going to always want to kill the higher by that.
Even though a dagger reduced.
No, the aggregate reduce is always dependent. Yes. For this, you don't need to do the right stuff.
And is it? Are you saying that this functor and the RAM satisfies
Descent properties, yes. You're going to mention at least one kind of descent properties here.
But I vaguely remember that in this situation, actually, is definition like that.
Yes, but fortunately here, because you replace this formal completion by this, some of these problems actually disappear. This definition is, let's say, has much less problems than this. Particular, you have a lot of descent. Some of the properties. First, given in general, you can extend this actually all these objects, just stacks generally by one. Yes. Particularly, you can apply these to classifying stacks, to quotients of Ricci spaces, to perfect order spaces as well, or to adic spaces. Yes, I just took the example just to. And apply this to, again, more general analytic steps. So if you have one of these bounded algebras, you can actually construct a logical space. But let me just denote it by the spark. So a way to construct this logical space, or maybe not in the sense of prover, but version to construct this, you just take the all limits of A, where B is the usual data algebra. P, and just take the usual spectrum of P. Looks like an ad hoc definition, but is what it is. Let's say that basically in any other adic space that you know, or perfect spaces, pre-perfected rings, this is the way you will end up constructing the adic spectrum so-called. You just have a bunch of functions that you evaluate and do some evaluations that are equal to something. But at the end, the way you compare rational locus is always factored into a data algebra because you only compare apparently many functions at the same time. So this definition is as fair as the other definition, at least for adic space.
I have a question. So is A given? Does A have an analytic ring structure?
Yeah, maybe taking something like the minimal kind of thing you can put here. So, I mean, you can put additional analytic ring structure and actually create a span of A on this slice. If not, you can think about this as basically just I don't know how to call it here. Just something like this. With kind of the maximal compatification, this adic compatification of this like that. They're not trying to complicate things by putting an additional groups.
But actually also a related question. And so in the drawn stuff, is it just one? There's no analytic ring structures that one puts.
I mean, for this definition, that would be enough for us, not. But there is a version you can input this further. So for us, let us just not care too much about this kind of geometry. And maybe just the following, so the spectrum of issue data algebras. And for this spectrum has a maximal output quotient that we call the Berkov spectrum. Also, a way to define it is just the rank one valuations at the level of data algebras and take the same limit here. And we have a map distance from the spectrum of these rings of this Berkov spectrum. So this means we can localize the formation of this guy using, well, actually we can use this the adic spectrum, but at least let's say just use the Berkov. This means that for a suitable, maybe not open but closed or convergent neighborhood of a disk. So here you can take the pullback here. This is going to give you a rational localization, maybe a Berkovich version of a rational localization of a ring there. If again, this one can be somehow promoted to the state algebra, but maybe in a different language than this. And it's telling you that in the usual rational localization you found in bridge geometry in data spaces, you can somehow encode it in a map of stacks. Maybe a slight variation. In particular, just by gluing along these pullbacks on opens, you can define a notion of the right body spaces, of the right code spaces. It's an honest map of anti-stacks. That one is an honest map of anti-stacks. Yes. Yeah, the one with the star is actually just the local map. That's why I wanted to write that. So this is number 1. 2.
And is this MA the same as like the analytic vector?
Yes. I think it'll be the same. So we can glue. These guys along the Berkovich spectrum. Construct something that we may call just the right one. We just say, these spaces. Give it the Berkovich spaces.
The right because A is
Because it will be at the right region. Yes.
and
How do you regard MA as a?
Maybe not give a complete answer for that, but just say that you can always see any condensed animal or condensed set as an analytic stack, just by declaring what the profanates go, and then using descent, and the profanates go just to the spaces of locally constant functions in the base. Okay. Then you just kind of do this.
Yeah, but so this, like saying that you have a map of analytic tracks in this way, since it's compact algebra, is that correct? That this
Yes.
is basically equivalent to saying that you can localize A based on these. Basically, that you can do these localizations based on inequalities.
Yes. So this one has some kind of shapes. Basically, for each open close, the pullback is going to be drawn open close to the space in the potential flow. There are concrete ways to realize these kind of maps, but basically, for us, basically means that for any open convergent ball is going to give you some kind of localization as a rational localization in the usual sense of the data.
You are very strict trying to say like for any compact of state and that's the yours are analytic stack.
Yes.
Certain functions and then this is very.
And then you end up with a map like that. You construct this. Maybe again, some last remark is that, well, we have this notion of Laguerre radical. Then we could ask what happens about the topology. Like if you take a scheme and you take the reduction of the scheme, they have the same underlying topology. So what happens with this one? So it turns out to be the same. So let me be about to that diagram. Then, well, the span, let me just forget the span, just write the copy spectrum. These two guys is the same. Conversely, let's say, if A is sans rejection on the algebras, then let's say under some technical condition, that in the order refined situation we're going to work is going to always be satisfied. If we have an isomorphism for copy spaces, then actually the reduction of the two rings is this means that actually this reduction is the maximal quotient of A in this world of bonded rings that have the same underlying copy space. So this is something similar to points for the right geometry. The reduction is the maximal quotient of the rings that have the same spectrum.
Understand the syntax. So it's a
Yes. So
then
under some technical condition,
if MFA, if it's induced, it's
yes. Then actually the reductions are the same, meaning that the reduction is kind of the universal quotient that if you want homomorphism. Zariski closed with space that is kind of homomorphism.
Just wanted to clarify, so the construction of spa A is in terms of sort of classical takeout. Is that right?
Yeah.
Okay.
Yes. Yes. You can use just classical data. I mean, you could try to use like arbitrary Uber rings, but you end up with the same definition because for Uber rings, the spa is also the same as the limit of the spa statement.
I guess it just meant that one doesn't need like some more general, like solid.
No. Just we take that derive that suffices. Okay.
Sorry, this point three, is it also true in like the classical approach, I think? Well, when you replace dagger by just the ideal of non-zero for
These things, I'm not pretty sure. I mean, imagine that the nil radical is the same as the norm zero guys in the usual coefficient. So it's possible that yeah, it's already like somewhere in the
that's right. So you said. So I guess this MA can be interpreted in two ways, right? Because one is that you have like the topological space of the classical spectrum, right?
Yes.
And then you can consider continuous functions on this, and you can take another spectrum associated.
Yeah. So this is not.
But also you have like this analytic stack of norms on.
Yes.
On A, and you have this analytic Berkovich stack. Is this the same as?
When like using the stack of norms, you can construct always a Berkovich spectrum that touches this norm, and this one is going to correspond to that construction for the norm coming from P. So maybe just say that is that this guy will be so horny. It's not this spectrum of continuous functions on that. Okay. This one is constructed in a slightly different way because you want to localize it. Maybe not explain what is constructed, but what is important from this statement is that you have this kind of map going to be subjective and you can localize using just open subspaces of this. But yeah, it's not the same as continuous functions. It's more constructed of maybe just let me say what the category of shifts is. This way. Category shifts in here is not going to be like modules over some continuous map. Instead, it's going to be the same as the category of billion shifts, maybe in solid cubic. So the right category of a billion shift in here is solid cubic. So it's a different category of what you will get. You get a billion shifts. Okay. So, well, having introduced this class of nice rings, turns out that, well, at least somehow motivated from what happens in the usual periodic prismatization, we know that the prismatization functor actually satisfies stronger descent properties, in particular quasi-symptomics. And in the category of P-complete rings, we can find a very fair class of covers or objects that cover the P-complete rings in the quasi-symptomic side, which are the so-called semi-perfectory rings. So now in the following, going to introduce a class of rings that is going to play the same role and essentially are the same as these semi-perfected. These are called, at least so far, organically perfected.
So, to take a break now.
Yep.
It'll be a little bit early, 5 minutes earlier than usual, but I'm just tired. And
Yes, you can take a break now. Okay, perfect. So as we were saying, we want to find how this kind of bonded rings, but at least for doing rigid geometry, complete geometry is reasonable. But still, we want to have some kind of class of rings for which should be enough to test to define the prismatization and get anything else from the sample. These rings ought to be an analog of semi-perfected rings, let's say, inspired from what happens in the P-complete situation of prismatization. It turns out to be actually not far from that. So this is what we call these nil perfected rings. I can just give you the definition right now. So let A be on the QP algebra, then we say that A is nil perfected if its reduction is a perfected ring. Basically, we just allowed some kind of nilpotent thickenings in this sense. Perfected rings to model our category. So let us give, or maybe sketch just a couple of statements that actually imply that this category of nil-perfected rings is the analog of maybe a slight generalization of the category of semi-perfected rings, and that at least any Banach algebra, maybe of this, any Banach algebra can be covered by one of these guys. Theorem. So let B be a semi-perfected ring. B. So this means that B is a quotient of perfected Q algebra. And then let
so can we just do it and have in what world we are?
Q algebra. So it's just a quotient of this. It's just going to be a quotient of this one. I mean, usually you call it a Banach quotient maybe, but for us it's just enough to be a quotient. If you want, it could be just the generic fiber of a semi-perfected ring that be complete algebra. You just want to have a quotient of a for QP. There's going to be a quotient of a perfect ring. I don't
No condition.
No condition.
What you think.
Still, I can well, any semi-perfect ring. So it's going to define some heuristic closure space. It's called K. The fourth B. So it is space. So basically, just given by a bunch of equations in the ring A. And well, given as a closure space, theorem of Penlayan was then reproved in Bad Scholz's prismatic homology. There is like a maximal final perfect of the space mapping to the A, the spectrum of A that factors through these sets. And this spectrum of space is called the profession. So we can take a curve. And well, for this, actually, it's not important for the algebra B to be a Banach algebra. You can always like factor through the Banach quotient of this, even by putting out the deal, they find the perfection. So this by Schulze,
So you mentioned imperfection, in the sense of
maybe say maybe just following back Schulze. This one. Then based on then the reduction of this guy is exactly given by this curve.
So in case one, the ideal is defined integrally and understand. Is that always the case? Or you have a right to that?
I mean, you can always arrange that. I mean, you can just take the intersection of the kernel of this with the elements of bounded elements. This depends on ideal, and you can just pick complete this ideal and get a pick complete ideal in the pick complete. And for this statement, is not going to be. So the perfection is maybe just going to be the perfection of the Banach quotient. What matters is basically that you have a maximal statistic space, give us some equations, and there is a maximal perfectoid guy, which is a maximal quotient of A, which is perfectoid, a minimal quotient of A, which is perfectoid. Well, basically the same spectrum of the statistic spectrum. This is kind of the table. You can make it work in this sense as well.
Is the definition is that just a definition of dot five?
I'm just taking things on the underlying ring, and everything is a quickly solid algebra. Yeah, this is just depends on the underlying.
Well, wait, sorry, yes. I mean, it would be possible that like A could have some like some invisible stuff that's invisible on the underlying ring.
This will have this A plus behind, but for these definitions and for the near radical theory is actually relevant to have these additional solid structures. I think that's.
Oh. Sorry, I think in relation to the question, I mean, is it a purely algebraic condition on A, the underlying ring of A, or
I mean,
A as a solid?
Maybe, yeah, solid QP algebra. Yeah, it's an actual, yeah, solid condition. Oh, so I kind of already told you what the proof of this statement is. Let me just sketch a proof. So by definition, one B perf is the quotient. And here is what let's say Schulze, what Laya appear of A mapping to here, such that the spa of the perfection mapping the set is going to be an homomorphism. So it's like the maximum, the quotient of the perfectoid ring, which is a perfectoid, making an isomorphism with the zero set, the ideal depicted there. But then I told you that for any bounded algebra, which is any co-limit of rings, in particular this was the maximum of the algebra, there is a spectrum. And the spectrum will behave as respect. The spectrum of some statistic quotient, or some quotient in this sense. So in QP algebras, it's just the same as the zero set of the underlying ideal usual set. So this map, which is going to be a projection, because already mapping to 8 into that is a projection, and this is an ISO on topological spaces So by the remarks we did before, they have the same reduction. Every remark of these spaces that have the Zariski quotient, the Zariski closed space with topological space, they have the same reduction. But this guy is a perfect Euler space. A perfect Euler spaces are already reduced. So indeed, we have the reduction. So indeed, at least from this point of view, this notion of nil perfectoid is actually a generalization of the notion of semi-perfectoid ring. The sense that any semi-perfectoid ring, the reduction is basically the perfection. Yep.
So this is combined as thing is that this proof is very easy, right?
Yes. The hard part is basically that shows the light. Okay.
Yes. So the hard theorem is liable.
Yes.
And this is not a. So it's a proposition.
Well, modulo setting up all the theory.
Yes, modulo setup. The really good theory should be.
Fair enough.
Is there an a priori reason why the dagger reduction is automatically perfectoid?
Without using this,
Yeah.
I told how to prove, but I think it's wrong. Yes. So maybe I don't know, conjecture. Let B be semi-perfectoid. Such that, I mean, without proving this, or maybe just prove the proposition. Not from, I don't know how to write this. Exercise. Challenge. Position. Without using but short serial crypto. Basically prove that the dagger quotient of this guy is perfectoid without appealing to these theorems. And it means what you need to prove basically is that the power bounded elements in this ring are incomplete. That's it. So this is the first proposition saying that everything, I mean, that is a general semi-perfectoid rings. And the second proposition tells you that any Banach algebra can be covered by one of these guys. So let any be a Banach algebra. The algebra. Then there exists a descendable cover. Again, the descendable is going to be the kind of maps that are epimorphism. Descendable map of A to B with B being semi-perfect. Maybe I'm going to explain the proof with the sketch. Basically, just take K roots of all elements. A, one of them what happens in the actual incomplete situations, you just take the data algebra to take integers of the data algebra, and this map is actually descendable. So you just these integral variables, and you can discover something bad. So for us, finally, the category of analytics that we're going to consider let me something. category. Right. This is some kind of the opposite category of this. The category of analytic stacks. Here is maybe three stacks. And since I still don't have a nice name for this, a good name for this, let me just call it nice. And these are just pre-chips on this near perpetuator. At the end, once we made all the constructions, we are going to ask how much descent the construction will satisfy. The final category of analytic stacks will be some shift or suitable topology, basically given by this kind of covers.
But in the left hand side, you also wrote pretty.
Yes, I also wrote pre. The construction is much better to do at this level and then figure out how much descent we can actually say. So we're going to live in this world, and basically by this statement, any reasonable analytic space, in particular the pure Banach space, it's from Banach algebra, is going to be representable in a suitable shiftation of this shift. So we can then continue with the actual definition of the prismatization. So we already have the nice category of that is going to model our geometry. Let us continue with the category of Prefontaine curves, or the analog of delta vector.
When I say this map is decidable, in particular, it implies like the direct category of A is given by the direct category of spectrum.
Yes. For this, recall.
Is it the category which you know by F of
Yes, it's going to be the category of delta.
I'm not sure that you find it, but at least you give it.
Yes, and this is actually a category that we're going to define right now. So recall for S some perfect ring characteristic P, perfect spacing characteristic P. We have several constructions. We have this particular this y0 infinity that we're going to do S. Which is just the kind of the span of S modulo the locus of the cell uniformizer vanishing and peak vanishing. And well, basically, discussed this the last time. You can define this locally for affinoids, and then you just glue it together.
Sorry.
Yeah, this is just y of S, and this one is just making the interval where it maps to. This is simply mapped this interval 0. This guy is not just an adic space. It has an automorphism. Then, well, from this construction, well, something that came natural after I either realized that it was natural, that at least once you look at the right, is something natural to consider. Is just somehow okay. We have a nice category where we can do a lot of reality theory, which is precisely perfect on the spaces, and for these family of Prefontaine curves, we know a lot about them, thanks to the work of Sparg, Fontaine, the work of Chaucer, and many others as well. And well, we would like to extend this knowledge to a suitable category of adic spaces. And what can we do? Well, similarly, what happens for crystalline sites or infinitesimal sites, we can just start adding nilpotent elements to this one. Definition. Generalized. No. Maybe B. Separator. S, Y, S dagger, Frobenius, where we fix again our knowledge in characteristic P, perfect space P. We have some kind of nilpotent thickening. This is like a rather space that we had before. Well, basically, this is going to be a closed, statistically closed immersion, and with same underlying topological space. And yes, great. Well, a Frobenius on this guy, such that we have the following. Well, I mean, it's not short that it's the data of these two data. Frobenius and Frobenius S.
Somehow the deal is zero, but what is here?
Basic closed immersion. So locally for raphenoids, it's just given by a quotient of rings. Plus ISO topological spaces.
Just so
This is not far from being a nilpotent thickening in usual algebraic geometry.
yes. So geometry where the function or you could apply it in every kind of
Yes,
here it looks more like
the second one.
this second.
Yes.
Uh,
Since well, there is not like
maybe
order on
it's-
nilpotency,
Maybe it's better to put it
but
I'm not insisting, okay, it's just some, it's shorter.
yes, that's true. You're trying this.
So but it looks more like
A nil thickening. Right. Dagger nil thickening. Okay, not like this, but
Somewhat analogous to like a delta ring since it might be semi-perfect.
yes. So let me go. Where did this definition came from? Why this definition? Oh, well, maybe let me first finish this amorphism of generalized Parkinson curves. Yes, it's dagger Frobenius, P, YT dagger Frobenius 2, 1. Well, is
just so P, so P is a map from. Yeah, since I don't understand anything, I'm asking formal questions.
yes. Like this space is also it has a Frobenius as well. And this Frobenius basically just lifts the Frobenius you get in the usual perfect function.
Extends. So
So this is first a map of perfect spaces. That automatically is going to induce a map.
just and what is just an extended? So P is just an extension.
It's just an extension of the
And
Frobenius.
PS, what is the meaning of this? So you also wrote with something, some symbol that.
It's just the commutes.
So it's commutativity, nothing.
Yes, it's just that it commutes, like, which is, let's say, because things can be derived, it's actually additional stuff. Yes. But this is why you need to actually keep this thing compatible with. So you have a map of perfect spaces, the underlying perfect spaces, which is kind of a map of the reductions of these guys. And of course, a map of these guys lifting these maps. Are P equivalent. you just get a map of the vectors and basically the equivalent maps of these important thickenings that kind of extend the already existing maps in the perspective. We let take a tilde be this category. Of again generalized.
So the construction of the dagger unit radical,
Yes.
it's loose, right? So can you think of it as like a sheet of ideal
General may not be true, but it's true for these ones.
for this one?
Yes, it is true whenever you have spaces where the Zariski these localizations are still, let's say, uniform. For example, perfect super spaces.
Okay, so in
Yes.
this case, can I think of this dagger nilpotent thickening that I have some like sheaf of ideals associated to this closed version, and that the map of this sheaf of ideals into the structure sheaf is going to factor through the dagger nil radical of.
I mean, in examples, is maybe the nil radical is going to be an ideal of this, but this general definition could not be a module over these guys. Could be something else, but it's basically just again, you have this in superfected rings, just the gluing of these Banach algebras defined this YSS, and for each one you just add some nil radical. That because these ones are nice, like superfectoid, the nil radical is going to also just localize for the analytic topology. So you just have a gluing of all these guys.
I was asking like about formalizing this notion of dagger nilpotent thickening. So if you have, I guess, closed immersion, you're going to have an associated ideal shift. This, right? So this is like equivalent to this ideal shift associated with closed immersion. When it maps to say the structure shift of YS dagger, it's going to factor through the dagger.
This is always going to factor, like the nilpotent things are always going to factor to nil radicals. What you're saying is that actually
They're like equivalent to same dagger.
yes, you basically want to say that this one for any affinoid is the same as its nil radical. Yes, like this ideal defined distinct just the nil radical, meaning that basically the nil radical is going to localize this. Okay.
If you just release
Yeah, so that's why I took this. I also removed the Lucas when P is equal to 0. Yes, because mod P is going to be much more challenging. I will still have to figure out completely how to define this one.
Just to make sure here, like what category is bias, right?
What category is what?
This bias or bias class.
Sorry, I don't understand.
The second term, bias class, or bias dagger, sorry.
YX dagger.
Yeah, so
What is this?
what kind of space is that?
It's a derivative space. I mentioned before that you could glue these bounded rings in the analytic topology, and you could define a notion of derivative space. So this one is one.
This is the divide addict space using the gluing convention.
Yes. Again, basically, you can think about an initial again, just kind of have a Berkovich spectrum for which reasonable small enough of flows inside an open, you have just a ring, which is a bounded ring, and you can't localize it. Why this? So let me maybe make a position for construction first.
Why? What do you mean by why is this?
Why this definition? Let me do the following construction. So let S be a unique perfected. Characteristic 0. Maybe let me just write this dagger just to mean that actually has a important thickening inside. And let S be its reduction. Perfect ring characteristic 0. So, well, you could, I mean, some feature that we have from perfect rings is that there is some kind of an universal map given YT of S, generalized object field.
And say reduction, this means the reduced.
They just keep the inequalities.
Not
monolithic.
No, no, no. And some maps from this guy to this guy. Well, you may wonder if there exists some kind of adjunction between kind of universal object in here that just leaves the something here. So actually, you want to construct. I want to do the construction now. Universal. Why? This dagger that you can think of is kind of the Carpenter cube attached to this mid protected guy in this category. Such that the Carpenter's S dagger mapping to this guy, but map to this. Yep.
Why is that in Dotson?
Is a map of what?
Is in two, is that not part of the Dotson?
Yes, this map is part of the diagram. Yeah, the whole diagram is part of the diagram. I mean, this one is already kind of a copy this guy. So again, you may wonder if there exists a kind of universal way to construct a map from some Carpenter cube to general Carpenter cube to this one. And it turns out that there exists. So the answer, oh yes. What was the question? Indeed. Well, the first thing is that you have a map from the reduction of this guy to the reduction of this guy. Like that. This one is perfectly, this is a curve. And this map is equivalent to having a map, basically S flat to T flat. So the map from S to this Carpenter curve, because we're already in characteristic 0, is basically the same as having a map from S flat to T flat. So then we can extend at least this map when we reduce to this guy. Into just this extension at least to the curve. And this map is built right. But then you have a bunch of important thickenings on each variable S. And again, if you want to make this universal such that this is P equivariant, then well, you can basically just have a map. Maybe probably this map may be I, this one F. Just adding this Frobenius translates of this inversion. It's not, but it has not from these guys. All these plates. From the natural map. This was given by all these Frobenius translates of this map. And then, well, you can just take the push out of this diagram. And this push out is going to define some space that is just an important thickening because of the level of algebras. Basically, just took a product of algebras in all these guys. And this one well, is going to be this like universal construction here. So indeed, this forgetful map from Carpenter cubes into analytic stacks is going to have a left adjoint. Just given at the level of affinite, the level of this main perfectoids, by take this push out, which is kind of the way. So the way this relates with bit vectors, which is maybe the reason why we take this construction, is the following procedure.
Sorry?
Yes?
So in the right side when you write the condition that you want for y as letter. So don't you want to say that also S is going to factor through YT or something like in the definition of this universal property? Because
S is going to follow. No. You just need to. No. I mean, S is automatically factored to YT because it's reduced.
Okay.
Then maybe motivation. Or bit vectors. So let our near perfectly bring over to P and let add its new reduction. Then, as I said, you can consider the algebra functions of elements of degree 11.1. Have a triangle, micro diagram, over sequence. The elements of norm equal to 1. In the case of the perfected ring, the elements of norm equal to 1 is just the bounded norm over 100 guys. And here in the quotient, you still have the bounded value. So then the first attempt we tried to do this was, of course, using like bit vectors coming from mathematical homology. So, well, because if you take the bit vectors of R, it's a product of R's because in characteristic 0, maybe there is something to do with the bit vectors of its power bounded elements. So otherwise, it's very trivial. So we took these bit vectors.
There, I don't see once.
Yes, the near radical of R mapping to the elements of norm less than or equal to 1. A mapping to the elements of norm less than or equal to 1 of the perfect ring, which coincides with the power bounded elements of the perfect. So then take bit vectors. This, so it's an ideal, you can take bit vectors of an ideal. There is some bit vectors here. Bit vectors. The first attempt we tried to do the prismatization, maybe coming from motivated from a definition that Schulze gave the summer last year, which was taking some kind of perfection, the prismatization of what Lurie and Greenfield. Well, we tried to do this definition and take this perfection and see what it gives. But maybe let me do something slightly more smart that, again, came from this kind of motivation. So this ring is perfectoid, we're taking its bit vectors. So actually we have a map from 9 to flat of this guy into here. We have this map, and then we can try something like this double branch. Maybe just let me call double branch, which is going to be again the other hand. So again, we are in characteristic 0. So the near radical is actually a QP vector space, always divided by 2. So the bit vectors is just going to be by using the ghost components. Product of the near radical. Then maybe leave us an exercise.
I don't have time to. So first of all, the upper row, W of nil there. What is the second?
It's just a price, meaning that they just took a pullback square root.
The W prime. What is W prime?
It's just the pullback of this map, because I don't have another name for this. Yes, it's just a name for it. So exercise. If I take this W prime R,
Can you give me time to rewrite this? Just 18.
So both rows are 5
Let me maybe just change the course, right, the exercise down.
In the upper row, the inner of what?
Of R0 flat. So just that of R naught. It's a perfect ring, it takes field, so take the I for pixel. Maybe just the same of the D vector. Or again, just put what I for R0. So I is always the one of them. So then exercise. If you take the analytic spectrum of this W prime R, where you inverted, so then you have P, if you use certain information with P roots, then you can always leave this Cooper diagram. And then you kill, when you remove the part where the vanishes.
Just on the other hand, W of new the R, what is written there?
It's just yeah, the bit vectors of this new radical. Because it's a QP vector space.
But what is the?
It's just a product.
Yes, and below W of new R, what is this?
Ghost. Ghost component.
Ah, good. Can you remove H?
Can I write it H?
Just shift it to 3.
Ah,
positions.
GHO.
Oh.
GHOST.
Wait.
3 positions.
Sorry.
This is the level of my investigation. Something coming at those.
Yes,
Not
sorry.
close.
I have all- So take this guy, this construction, and remove the locus where the setting meister that you leave again, and P vanishes. And well, you end up with just this Y construction attached to this need perfect.
You said you and F.
This is just equal to this. This is defined as this push out that I just described here.
So just make sure that the right vertical map is steerable. It doesn't induce from off.
This one?
Right, the right vertical map, like doesn't induce from projection to the zeros coordinate.
No, I mean, whenever you take these vectors of a perfected ring, of the P complete perfected ring, you always have one from any of that. Because, well, I think one is going to be the perfection. This one there is the perfection of this bit vector. You take a P complete perfect ring, you take the bit vectors and its perfection. This is the same as taking inf of the perfect ring.
When I say perfection, you mean
Limit by Frobenius.
inversely.
Yes, inverse limit by Frobenius.
That's really not.
Okay, I don't know. Yeah, okay, maybe it's the limit by
Not
Frobenius.
very called perfection.
Pardon. So again, this definition of this general perfect vector, we started with this maybe more complicated constructions in bit vectors, but at least over QP turns out to be much more simple just by these important mechanics. At least geometrically easier to write down, even though you still have some complete formulas.
You were saying that we start with these vectors, but then they are not too necessary.
Then at least over QP, still not QP.
Yes, let's
See, over QP, because of this kind of construction, turns out that whatever the theory you're going to construct in bit vectors is the same as the one you just constructed in this more geometrical block. Still, you can use that to compute, but I'm saying that at least geometrically, this one is at least for me and for us, it's easier to prove things using that. I think this is more a subjective thing.
Yeah. So. here is the situation. In the usual theory of prismatization, using weak vectors. Well, the problem in the theory that you are explaining, the problem, at least for me, is that I don't understand the prismatization, for instance, of it. I don't understand the prismatization of the fine line, or maybe the prismatization of the closed disk. I don't understand this ring stack. You will give some kind of description,
Well, which are
but already I don't understand the ring structure, and in reality we need a little bit more than the ring structure. We need not only the actual class. Additionally, we should understand. But we don't understand multiplication, and we really want to understand the action of any holomorphic function,
yes.
any holomorphic operation, and maybe not even binary, but any number of actions. And on the other hand, in the usual theory of prismatization, the magic of weak vectors somehow gives you this image.
Yes.
And my hope was that I'd like to that maybe if one uses weak vectors, some version, then we'll also see the ring structure and the
Yes, and maybe let me answer that.
but you
Yes.
you are trying to get rid of. You are saying that we are happy that that we don't need that something can be described without it.
Yes.
However, I still agree that it's still a problem to describe to give an explicit description of the information, let's say, of the disk, which exhibits this ring structure.
Maybe what I want to say is that we started thinking of the prismatization using bit vectors, and even in the case in Frederick 0, we are still using them because we don't know how to do this construction. What I want to say is that maybe we're not getting rid of bit vectors completely. We're just replacing bit vectors by this construction, which is just a more geometric way to think about bit vectors.
Okay.
Which is still giving you enough information to recover all the structures of my print stack.
Yes. This is good. Now, here is the problem for me. So you are defining the prismatization as a fact. You will describe the prismatization of n, let's say n digits. But my goal is much more modest. I want to understand the situation of the unit. And the question is, after all this great theory, do you know description of the situation?
Yes.
The unit disk, which exhibits the ring structure.
Yes, yes, yes. So again, this is going to be a maybe not so explicit stack in the sense that, okay, it's going to be as explicit as the values in these rings are. Which, if you want a way to say that, is basically just, well, I didn't finish the definition, and maybe I don't have the time to finish the definition. We're going to define the degree one divisors in this category. And the ring stack is basically going to be given by this bit vectors, this b prime, divided by this degree one divisor.
So will it be
Which
eventually will it have an explicit description as a will it have a description as a closure of something explicit? Explicit analytic space by an explicit.
so, I mean, like this GA prism in a perfect ring is going to be the occlusion of this ring by some which is a degree one device. So
It's a function of this ring. Yeah.
by Cartier device result, degree one device result. Okay, haven't defined the next maybe not good.
Okay. So this is good.
The magic is that all these other descriptions I gave before are not coming for free. They are coming because still you are in this geometric approach, and in the geometric approach, you will have access to Banach corner spaces. And this other geometric description, the prismatization I wrote in the example before, is coming precisely because of this theory of Banach corner spaces. This, again, also encoding an important part of all this business, even though maybe it's not at the ring structure, still that would be relevant for applications, all the stuff. Yeah, sorry, I think I should finish, even though I didn't define the optimization, but I did good process.
So maybe so your goal is to define. So we are close to the definition.
Yeah, we're just
And we will see the next slide.
yes.
But again, we will also explain something about the specification of the fine line or the specification of the disk ethering together with the ring structure.
Yeah, in particular, we're going to explicitly describe the whole space factors. Right, space factors.
Yes, I would be happy to understand.
Yes, going to be again some kind of extension of GA, but with GA daggers. Again, you can write down these big vectors.
So are these just usual big vectors or something?
In this case, it's just the usual vector.
Just the usual
Yes. Yeah, for extending these things to be equal to 0, it's going to be 4. So for the extension of the prismatization to characteristic P, sorry, there is where fancier version of big vectors start appearing.
So you're saying that the so vectors are
Enough. As long as you take the big vector of the correct wings.
as long
As long as you take the big vectors of the correct wings, meaning not of the whole ring, but of the whole data elements. Otherwise, you take just the product of it. Yeah, of course. That's the only constraint.
let's say this week.
I have a couple of questions. So one is, in what you're explaining here, were you saying that this approach via generalized spark protectors and via bit vectors are equivalent?
Yes.
So one can use either to define the
The
analytic.
definition at the end, you can use one of them, yes. And the reason is because using this approach, once you geometrize this construction, you just get the push out that you got here. So the joints at the end, when you compute the vectors, are just the same. So when you compute the prismatization, are the same, and they're going to give you the same theory.
So in the algebraic theory, in theory for photon schemes, the prismatization defined for all rings has advantages in that it, for example, lets you see additional symmetries of the theory. But you were indicating that you had reasons to prefer the approach analogous to the approach via delta rings in your setting.
I'm saying that we're using both approaches. We're using both the one vector rings with these general hypercontent curves, and saying that the theory of V vectors that is used here is replaced by this left adjoint construction, the level of spaces. But again, like algebraically, it's carrying out the same information of these rings once you localize. So it's still like using that same approach, but in a different perspective, more geometric point of view.
I mean, I guess another comment is that the Nygaard filtration can be included using the stacks on the Z vectors.
Yes.
Perhaps it's
Yes, this thing that we have discussed, may not come from the category of delta rings. So still, if you would like to have such a kind of geometric approach, you still will need to change the things around. This category of harmful curves may be something different instead. And maybe a more reasonable approach would be just to attack using this, or still hoping that there is some geometry you can work with. But yeah, so far we don't have this little version of prismatization.
Other questions?
I have a actually more basic question. Just about this notion of the dagger null idea. So is this a notion that's stable under both arbitrary products and like filtered polynomials? Or let's say a diagonal potent thickening of bounded. Oh, maybe is a product of bounded rings? Bounded.
Yes, yes. So okay, maybe something to mark, maybe just to mention is this category of bounded rings also has limits, so the limits are computed differently. That the QP has limits, but a limit in this category is given by take the limit, like the connected part of the limit. The guys of normal equal to 1, then we move. So this is going to be the limit. What else? Like I don't know. If you have a map bounded guys, and the new radical of A is going to land in the second element of B. So it may not be true that the nil radical of a co-limit is the co-limit of nil radical. And already an example of this is basically this function that overconverts 0. Like any T algebra has 0 nil radical because it's just a uniform T algebra. When you take the co-limit, this element T equal to 0, T, sorry, becomes just reported to this. So the nil radical construction is not doesn't come with little coordinates.
But just follow up, like here, the limit coincides with solid limit, or the limit taken within a solid category.
Yep, just an initial limit of
So
condensed.
that's different from just the inverse limit of Ri as within solid category.
I mean, taking limit of solid category is the same as taking limit of condensed. So
So what?
no. So that doesn't matter. I mean, the limit is the same in the solid category, in the abelian category, in the condensed category.
I guess my question was, if we just take inverse limit of Ri, not Ri.
Then this thing may not be bounded. And I got this example of this. We are not bounded ring, which is not a Boolean algebra. Take the automorphic functions. Define line. So the limit. This ring is not going to be bounded because you cannot, for the variable t, have some kind of section. This map is not. So yes, you take the usual limit, it's not going to be a limit in bounded rings. You actually going to end up being this limit instead. Makes sense, like just kind of taking it. So if you take this limit in here, I think you get something like 0. Yeah, you need to cover the limits.
Let's just think the speaker. Could you finish?